All right, so this is page 4 in the Algebra 2 packet and page 6 in the honors packet. I'm going to go through these problems pretty quickly, but in case you were stuck on any of them, you can come back and watch me talk through it. So square root of -7, well, following our pattern, that's going to be the square root of, square root of -1 times the square root of 7. Square root of -1 just becomes I, so the answer is I root 7, right? First step, break it out into -1. Second step, simplify the I. All right, here we're going to do that same first step, -1 times the square root of 81. -1, we know that that's I. Square root of 81, that's going to become 9. And when you have I times 9, we're going to write that 9I. Square root of 81, that's a perfect square, but if you didn't see that, you can always do a factor tree and break it up that way. All right, so for this one, we have a negative out in front and a negative on the inside, but we're just going to leave that negative out in front, right? -3 times the square root of -1 times the square root of 25. -3 stays there. Square root of -1 we know is I, and then square root of 25, again, that's another perfect square, so we're going to put -5, or just +5. Square root of 25 is +5. And we're going to combine all three of those terms into -15I. Okay, so these ones get a little bit more involved, but that is all right. We know how to deal with them. So we're going to do first step, as always, -1 times root 192. And now for root 192, we're going to need to break this up. So I'm going to go 96 and 2, and then 16 and 6, 4 and 4, 2 and 3, 2 and 2, 2 and 2. I'll circle all of that. So we have square root of 1, 2, 3, 4, 5, 6 twos and a 3. How many pairs of twos do we have? 1, 2, 3. So this is going to become 2 times 2 times 2 times the square root of 3. 2 times 2 times 2, well, that's 8. And then remember, we have this square root of -1 that's going to become I. Okay, we need to not forget that. And then what do we have left in the radical? Well, we had 3 sets of 2s, we pulled them outside. We're left with the square root of 3. So 8I root 3, there's your answer. All right. And for this one, you gotta leave the -2 out in front, times the square root of -1, times the square root of +243. For 243, you recognize it as 81 and 3, 9 and 9, 3 and 3, and 3 and 3. So we would have -2I times the square root of 3 times 3 times 3 times 3 times 3. You can see that we have 2 full sets of 2 3's here. So you can pull those out, and you have -2 times 3 times 3 times I times the square root of 3, or -18I root 3. All right. Keep it going. +5 times the square root of -1 times the square root of 252. 252, I'm going to go 126 and 3. I'm going to do 63 and 2. Go 9 and 7, and then 3 and 3. Now we will have 5I times the square root of 2 times 3 times 3 times 3. And there's a mistake here. Shout out to you if you saw that before I did. There should be 126 and 2, meaning that we should have 2 times 2 times 3 times 3 times 7. We have a pair of 2's and a pair of 3's, so we can do 5 times 2 times 3 times I times the square root of 7, which is 30I root 7. Okay. Now these ones can get a little bit trickier. Only kind of. So whenever you have a radical in the numerator and a radical in the denominator, you can simplify each of these separately. So -80, that's actually one that we did recently, right? If we go back to the previous page, we saw that when we simplified the square root of -80, or I guess we turned it into -1 and +80, we saw that 80 was 4√5. And go back here and follow along with that. So square root of -80 would be 4i√5. So on the numerator, we would have, maybe we have the square root of -80 over square root of 100. The square root -80, that's going to become 4i√5, right? And that's coming from breaking down the 80 in the -80 into -1 and +80, and then simplifying the radical, simplifying the +80. In the new denominator, you have square root 100, and that's a perfect square. And so, not 100, the perfect square of 100 is 10, right? Because 100 is 10 times 10. Now, we can cancel on the top and the bottom. Right? You can see the numerator, that's divisible by 2. The denominator, that's also divisible by 2. So we get 2i√5 over 5, right? Canceling a 2 in the numerator and the denominator to simplify it down to this. All right. Before we move on with this one, I just want to pause and call your attention to the fact that the cube root of that this is different from all the previous problems because we have a cube root, right? Every other problem on here is a square root. This one is a cube root. If you remember what we were talking about on this page, imaginary numbers are only used with even radicals. So for this problem, and this problem too, we don't actually need to use an I. And the reason why is because if we do our first step, right, break this up into the cube root of -1 times the cube root of +250, the cube root of -1 is not I, it's just -1. And maybe if we jump down here, let's explore for a minute why that is. So if we have -1 cubed, that's -1 times -1 times -1. -1 times -1, that's a +1. But we have this third -1 that'll make it negative again. So if -1 cubed is -1, then the cube root of -1 is -1. And then what we have to do is simplify 250, this cube root of 250. So I'm going to go 50 and 5, 25 and 5, 5 and 5. We would have -1 times the cube root of 5 times 5 times 5. And I made a mistake. That shouldn't be 25 and 5, that should be 25 and 2 times 2. Now our index is 3, so we're looking for a full set of 3. We see that we have 3 5s, and so our final answer is going to be -5, right? -1 times the 5 that we pull out, times the cube root of 2. Notice how there is no I in that answer, because it is an odd radical. Okay. Let's go over here, and we can do -3 times the cube root of -1 times the cube root of 324. We know we're going to leave the -3. Cube root of -1, that just becomes -1. And then we have to simplify 324. So let's go 162 and 2, do 81 and 2, 9 and 9, 3 and 3, and 3 and 3. So we're going to do square or cube root of 2 times 2 times 3 times 3 times 3 times 3. We have a full set of 3 3s that we can bring outside. And so now we have on the outside -3 times -1 times 3 times the cube root of, on the inside, what's left, 2 times 2 times 3. Okay, -3 times a -1. When you do a negative times a negative, it's going to become positive. So you're going to end up with +3 here. Times this 3, it's going to give you +9. Right, the two negatives are canceling out there. Times the cube root of 2 times 2 times 3. That's 4 times 3, that's 12. And again, notice how we have no I here, right? We have a cube root, we have a negative number, but our answer is positive with no imaginary component because this part becomes negative, multiplies with this negative, and becomes positive. Now let's look at the challenge question. It must be completed to get full credit. If p is equal to 3x plus 4 and v is equal to x plus 5, which of the following is equal to pv minus 2p plus v? So we have to do a little bit of substitution here, right? We know that p is equal to this, v is equal to that, so pv is going to be equal to p, 3x plus 4, times v, x plus 5. Right, so this term here, p times v, looks like this. Minus 2 times p, and p is here. So times 2, 3x plus 4, and then plus v. And v, we know, is x plus 5. All right, so here we have to remember how to double distribute. And it's essentially, I want to just do a quick reminder of this. I'm going to highlight this term. We're going to take this 3x and multiply it by that highlighted term. We're going to take the 4, and we're going to multiply it by that highlighted term. All right, so we have essentially 3x times x plus 5 plus 4 times x plus 5, right? You're taking this term and you're multiplying it by both of the individual terms of the first parentheses. All right, now we can just copy the rest down. 2 times 3x plus 4 plus x plus 5. And now we can distribute across everywhere that needs to, keeping track of our positive and negative. So 3x times x, 3x squared. 3x plus times 5, well, that's plus 15x. 4x, or 4 times x, that's plus 4x. 4 times 5, that's plus 20. Minus 2 times 3x, that's minus 6x. Minus 2 times a positive 4 would be minus 8. And then plus x plus 5. Now we need to combine like terms. So for x squared, we only have this one x squared term, so we're going to have 3x squared. For x's, we have 15x plus 4x minus 6x plus another x. So 15x plus 4x, that's going to give us 19. 19 minus 6 is going to give us 13. 13 plus 1 is going to give us 14x. And now we want to do the same thing with our constants. So we have 20 minus 8 plus 5. 20 minus 8 is going to give us 12, plus 5 is going to give us 17. And thankfully, that's an answer. So I think we did it right.